The initial spread index, or ISI, clearly identifies itself as the FWI system indicator for evaluating fire spread potential. This presentation will discuss where the initial spread index fits among the fire behavior indices, what affects the initial spread index and how it is estimated, and some of its common thresholds and important interpretations. As shown here in the FWI system flowchart, the initial spread index is estimated by combining the fine fuel moisture code and the wind speed collected with the solar noon weather observation. This standard daily ISI provides a good tool for comparing conditions on a day-to-day basis. This system of describing fire behavior depicts conditions ranging from smoldering to extreme fire behavior. Notice how fire spread changes in the descriptions as you move from lowest levels, rank 1 and 2 with little or no spread, to the highest, rank 6, where both fast spread rates and spotting spread are expected. Relating these levels of fire behavior to thresholds in the initial spread index will help firefighters visualize expected fire behavior each day. The initial spread index is the best indicator of daily fire potential in the spring in the FWI system, combining fuel moisture and wind speed. Notice that little fire spread is anticipated at an ISI of less than 2. Spread potential becomes significant when the initial spread index reaches 5 or 6. Fires burn primarily in the surface fuels with ISIs below 8. And extreme fire behavior is anticipated when wind and fine fuels drive the ISI over 10. Though the fire weather index system estimates an initial spread index at solar noon each day, it changes as wind speed increases later in the burn period. The initial spread index is a primary input to the fire behavior prediction system. This graph shows the respective roles of FFMC and wind speed in the estimation of ISI. Wind speed is plotted in blue, FFMC in orange, and the initial spread index is in green. Notice in this first black dashed box that though the fine fuel moisture code is at higher levels, the initial spread index remains below 8 because winds are low. In this second box, FFMCs are very similar to the first example, but because winds are higher, the initial spread index is much higher. In the third example, the initial spread index falls somewhat because the fine fuel moisture code is lower despite slightly higher winds. And in the last example, the initial spread index is very low despite moderate winds because of the precipitation that has affected the FFMC. Because the initial spread index combines both fine fuel moisture and wind speed, it's a powerful tool in describing expected fire behavior in a variety of applications. On the fire line, the initial spread index can be monitored to detect increasing or decreasing fire problems as winds change throughout the burn period. The initial spread index is used as a primary input for the fire behavior predictions for all fuel types. Because of that, using the initial spread index to define prescription windows allows the integration of concerns for a variety of those fuel types. Notice how similar the initial spread index in orange is to the NFDRS ignition component in green, though they are scaled differently. The NFDRS spread component in blue shows a corresponding but slightly different trend. The initial spread index expects wind speeds measured at 10-meter height, or 33 feet. Eye-level observations taken in the field are observed at a lower height, producing lower wind speeds, perhaps as low as 2/3 of the 10-meter wind speed. Most NFDRS RAW stations collect wind speed measurements at 20 feet height, though the difference measured in wind speed is generally very small. More importantly, wind speed is a function of the terrain and cover surrounding the weather station. Large smooth surfaces like airports produce higher measured winds than corresponding locations surrounded by forest cover like our fire raws. The National Weather Service forecast models for surface winds have a primary focus for aviation forecasting and generally represent those conditions unless specifically adjusted for rougher surface situations. Ultimately, when monitoring wind, be sure that you are estimating a wind speed from a height and from terrain and cover that the initial spread index or any fire assessment tool is expecting. The ISI table included in your field guide provides an easy method for applying the wind speed that you have measured, even if it is not at 10 meters. There are 4 wind speed measurement types offered in the table. The forecast wind that represents conditions expected in large smooth openings like airports. The 10-meter winds like those expected in ISI calculations. The 20-foot winds like those measured at most of our RAWS locations. And eye-level measurements taken in the open areas from fire line locations. You can use your wind measurements from any of these sources to directly estimate ISI in these tables. For example, if the eye-level wind is 3 miles an hour and the FFMC is 82, the ISI is 2. And in that case, the 10-meter wind would be estimated at 4 miles an hour. You'll want to note the 10-meter winds if you're estimating expected fire behavior. Summarizing what we've discussed about the ISI. Daily ISI as part of the Fire Weather Index system is good for comparing spread potential from one day to the next. Changes to the initial spread index should be monitored throughout the day, primarily due to wind speed changes. For best results, wind speed used in ISI calculations should reflect 10-meter winds from typically rough terrain where our RAWs are generally located. Simple tools for adjusting from other observing or forecast standards are provided in the field guide. There are other presentations highlighting the FWI system components and features. Consider viewing them as well.